The last time we saw a traveler from beyond our solar system, it was Oumuamua in 2017, silent, puzzling, and gone before we understood it. Now, in 2025, a new object has appeared, 3I-Atlas. Early size estimates vary widely, from an upper limit of about 5.6 kilometers down to a few hundred meters across, and we'll explain later why those numbers shift. When discovered, it was moving at roughly 137,000 miles per hour relative to the Sun, a speed that immediately marked it as interstellar. It's the third confirmed visitor of its kind, showing early cometary activity that contrasts sharply with Oumuamua's inert profile. Astronomers now face the challenge of studying it before it slips back into deep space, a task that began the moment an unusual signal appeared in Chile. A faint signal in Chile. On the night of July 1, 2025, the Atlas Survey telescope at Rio Hurtado, Chile, was carrying out its routine all-sky scan. Its wide-field cameras methodically swept the heavens, looking for any point of light shifting against the familiar backdrop of stars, most often near-Earth asteroids or long-known comets tracing predictable paths. But this time, the automated software flagged something different, a faint point moving in a way that didn't match the slow crawl of distant planets or the established tracks of cataloged bodies. Frame by frame, its displacement was clear enough to stand out from the usual finds. The system elevated the detection for human review, and astronomers on duty recognized it as a possible outlier. The object was given a provisional designation, a coded string beginning with the year and letters identifying the discovery sequence. At first, it was little more than a new entry in a survey log, except for its apparent speed across the sky. Detections like that often prove to be asteroids on elongated but still sunbound paths, or even stray high-orbit satellites caught in a deep sky exposure. But follow-up checks soon ruled out anything of that sort. When first reported, it was about 4.5 astronomical units from the Sun, roughly 410 to 420 million miles from both the Sun and Earth, well beyond Mars's orbit. Only a wide-field system like Atlas could have spotted such a faint object from that distance. Additional measurements refined its motion, and the results quickly began to diverge from the patterns expected of local objects. Pre-discovery images were traced back through archival data into mid-June 2025, extending its observed arc and sharpening the orbit calculations. Those calculations came back with an eyebrow-raising figure, an eccentricity near 6. In orbital terms, that's far beyond the threshold of one that separates closed, repeating paths from open, unbound ones. An eccentricity that high only comes from something entering the solar system at interstellar speed, and on a trajectory it will never repeat. Even so, early debate focused on what kind of body it might be. The first images showed no obvious coma and no tail, features that normally give away active comets when ices sublimate under sunlight. The steady brightness could have meant it was inert, like Oumuamua, which passed through without visible outgassing. But longer exposures hinted at the faintest of extensions along its track, just enough to keep experts from dismissing cometary activity outright. This uncertainty echoed the unanswered questions that had greeted both previous interstellar objects. Was this a fresh comet from another system, its surface ices intact, or a bare fragment knocked loose eons ago and worn smooth by its journey? Within hours of the initial report, news of the detection was circulating through professional networks. Observatories with clear skies, from Palomar's Zwicky Transient Facility to other Atlas sites, targeted the coordinates for immediate follow-up. Each independent set of measurements was logged with the minor planet center, reducing uncertainty in the orbit with every passing night. The trajectory was already clear enough to rule out an origin in the Oort cloud. Nothing gravitationally bound to the Sun could approach with its high inbound velocity. The numbers simply didn't allow for a local source. The process for confirming an interstellar origin follows well-established steps. collect multiple positional observations from different locations, combine the data for an accurate orbit, and check for any computational errors or alternative explanations. In this case, the sequence was completed with unusual speed. Just a day after the telescope team submitted the first official record, the International Astronomical Union released a formal circular acknowledging that the object's path was distinctly hyperbolic and unquestionably interstellar. The official name was set, 3I-Atlas, third in the sequence of confirmed interstellar visitors, I marking it as such, and the discovery credit going to the finding survey. With the designation came context. Oumuamua's visit had challenged astronomers to think beyond the tidy boundaries of the solar system. 2I/Borisov had offered a more familiar comet profile, bright and dust-tailed. Now 3I-Atlas, faint but measurable from hundreds of millions of miles out, became the next rare example. Its detection reinforced that the ejection of solid material from young planetary systems was not just theoretical. These objects were in motion around the galaxy, and on rare occasions, our orbits aligned to catch a glimpse. Even in the first week after discovery, 3I-Atlas was setting new marks. Spotted far earlier in its solar approach than any of its counterparts, it offered the potential for months, possibly close to a year, of observation. This stood in contrast to the weeks-long scramble after Oumuamua was already outbound and the more limited arc of Borisov. Early images captured it still inbound, well before the point of maximum brightness near the sun, giving researchers a chance to plan coordinated campaigns across different wavelengths. That July night in Chile became an example of how sky survey infrastructure can reveal much more than its original purpose. Atlas was built to protect Earth by finding near-Earth asteroids in time to warn of possible impacts. Yet its design, optimized for wide, repeated coverage of the sky, made it equally adept at catching rare, faint intruders from deep space. The same vigilance that might one day give us advance notice of a hazardous rock had flagged a harmless but scientifically priceless cometary fragment from another star. The confirmation set global telescopes into action. Proposals for viewing time were filed. Spectrographs and high-resolution imagers would search for gas emissions, measure the composition of dust, and track fine changes in light to infer rotation. Space-based assets would attempt to follow it in wavelengths Earth's atmosphere blocks. All this effort was aimed at wringing every bit of data from a narrow observational window before the object dimmed beyond reach. The speed of its acceptance into the list of known interstellar visitors carried an unspoken weight. In less than 48 hours, it had moved from a tiny, anonymous smudge in the Chilean data stream to a scientifically significant visitor with a permanent place in record books. That acceleration, combined with details about its extreme orbit and place of origin, would not stay confined to academic circles for long. And as word began to spread outside the observatories, the wider public would soon form its own first impressions. Safe but strange. When official confirmation of 3I-Atlas reached mainstream outlets, coverage escalated quickly. Headlines leaned on phrases like alien comet and visitor from another star, often illustrated with dramatic visuals of blazing impacts or fiery streaks against a night sky. For those only catching brief glimpses in news feeds, the suggestion was hard to miss. Something distant, fast, and strange was now passing through our region of space. Within hours, questions began appearing across social media. How close would it come? Could it penetrate the atmosphere? Was there anything to prepare for? Even its designation, with coded numerals and a nod to interstellar origin, carried an air of mystery that captured more than just the interest of astronomy enthusiasts. That reaction is understandable. Only a handful of known objects have been confirmed as arriving from beyond the solar system, and their reported traits, high velocity, unfamiliar makeup, paths unlike anything normally seen, don't sound like the well-behaved residents of our local planetary neighborhood. The fact that 3I-Atlas was moving at such extraordinary speed compared with any typical comet fed a natural, if misplaced, sense of alarm. It is not a visitor from the Oort cloud following a predictable inbound path. It is material once bound to another star entirely, now sweeping through an unfamiliar domain. From the very first orbital calculations, however, one fact was clear. This object would not come close to Earth. Its projected path keeps it between about 1.6 and 1.8 astronomical units from our planet at its nearest, roughly 150 to 170 million miles. It never crosses inside the orbit of Mars, meaning there is no plausible collision scenario. This was the core of the message astronomers shared early, replacing the notion of a risk with the prospect of a purely scientific opportunity. In simpler terms, it would pass well outside our immediate neighborhood, distant enough that its presence could only be felt through telescopes. This safe separation allowed researchers to see 3I-Atlas not as an object to guard against, but as a rare sample from elsewhere in the galaxy. In actual planetary defense situations, observation time can be diverted into urgent probability modeling or even theoretical mitigation strategies. Here, every available hour could be devoted to refining orbit estimates, watching the Coma evolve, and examining the composition of any dust and gas released along the way. Its significance lies partly in its rarity. In the whole of the observational record, only 2 confirmed interstellar visitors preceded, Oumuamua in 2017 and 2I/Borisov in 2019. Both shaped our understanding in different ways. The first showed no activity yet behaved like a cometary fragment. The second looked more like an ordinary comet but came from an entirely different birthplace. 3I-Atlas offers another variation, an active comet passing through at a safe distance, observable for months rather than weeks. This combination makes it valuable for testing how various kinds of ice behave when warmed at different rates and distances from the Sun. Being farther from the Sun at perihelion than most comets we track is not a drawback. In fact, it lets scientists investigate the sublimation of less volatile ices, processes normally hidden by more aggressive activity in closer, hotter comets. With sensitive enough instruments, signatures of different molecules can be read from the faint glow of the Coma, while high-resolution imaging can measure the dust output that shapes the tail. Ground-based telescopes with large apertures and space-based observatories that can reach infrared and ultraviolet wavelengths without atmospheric interference will both play a part. Communicating these details helped shift public understanding. Observatories described the event as a chance to examine material formed under entirely different conditions, essentially, a delivered sample from another planetary system, no mission required. Underlining that such events pose no danger in this case emphasized the value of the same survey networks that protect Earth from hazardous asteroids. They not only guard against threats, but also capture fleeting opportunities for discovery. That said, the descriptive shorthand of alien comet isn't entirely wrong. In the strictest sense, everything about it, its chemistry, its formation process, originates beyond the Sun's influence. Its constituent ice and rock condensed around another star in a protoplanetary disk that may have had a different balance of elements and radiation conditions than our own. At some point, a gravitational interaction in that distant system must have ejected it into open space, where it traveled for millions, possibly billions, of years before intersecting our solar system's path. Each observation taken during its visit offers a piece of evidence for reconstructing that long journey. Over the months as it approaches and then departs, attention outside the science community will likely ebb. But for those tracking it, the work continues until it fades beyond the reach of even our best instruments, leaving only data sets and refined models. Those records will stand until the next interstellar object appears, ready for comparison and ready to inform an even quicker determination of threat or harmlessness. Whether the next example shows familiar features or surprises entirely, each one builds on the framework established by its predecessors. What remains especially notable about 3I-Atlas is how the removal of any collision risk frees focus to examine its more unusual properties. Beyond its coma and tail, the single most striking feature is its motion, faster than anything gravitationally bound to the Sun. That speed is not just a curiosity. It is a defining proof that we are watching matter from another star system making a one-time pass through ours, and its pace is unlike any comet native to the solar system. An interstellar speed record. In terms of raw motion, 3I-Atlas is in a class by itself, even among rare interstellar passers-by. The fastest long-period comets native to our solar system, including those diving in from the most distant reaches of the Oort cloud, might achieve 40,000 to 50,000 miles per hour as they skim past the Sun. This is fast by familiar standards, but still far behind the numbers for this newcomer. From the very first measurements, its heliocentric speed was estimated at about 137,000 miles per hour, around 61 kilometers per second. That figure alone places it far above anything on a bound solar system orbit, and it carries with it something more telling, a hyperbolic excess velocity, or V-infinity, on the order of 57 kilometers per second. In plain terms, that's the speed the object would still have if you could switch off the Sun's gravity entirely, and it's the clearest indicator that it came from interstellar space. For comparison, a comet born here starts its journey from the slow drift of the outer solar system, gaining speed only through the steady pull of the Sun as it descends inward. The process converts gravitational potential into motion, but if you reverse it, the comet will slow to a halt at the far end of its orbit. An interstellar object does not fit this pattern. It arrives already in motion, with momentum acquired far from our system, momentum that no gravitational interaction here could have created. In the case of 3I-Atlas, that momentum is substantial enough to make its trajectory completely open-ended. That leftover speed is the smoking gun that this object didn't form here. Why it was ejected at such velocity is a separate question, and one we'll return to later. The bare numbers are striking in everyday terms. At its current stage in the approach, 3I-Atlas is covering about 3 million miles every 24 hours relative to the Sun. In that time, it could travel more than a dozen times the Earth, Moon distance. This rate of travel can't be matched by gravity-driven infall from even the remotest parts of the Sun's domain. It reflects a long history outside our system, one that has left it cruising through the galaxy until chance alignment brought it here. Its acceleration toward perihelion will push the velocity higher still. Like a spacecraft on a gravity-assisted dive, it gains additional speed as it falls deeper into the Sun's gravitational well. Any comet does this, but starting with such a high inbound velocity changes the scale of the outcome. Near its closest approach to the Sun, the final figures will exceed even the impressive numbers we see now, setting it beyond the reach of any speed record set by bound comets or asteroids. This comparison matters when putting 3I-Atlas next to its known predecessors. Oumuamua's smaller size and lack of visible coma made its speed all the more difficult to reconcile with a local origin. 2I/Borisov, a more familiar-looking comet, still arrived and departed faster than anything natively bound to the Sun. Yet in combining inbound pace, active outgassing, and a large estimated size range, 3I-Atlas stands apart as the swiftest active comet ever observed. As it accelerates into and out of the inner solar system, its path will be traced with a level of precision that pushes the limits of current tracking methods. That rapid motion has practical consequences for observation. Because its position shifts quickly against the star field, telescope mounts must adjust with unusual accuracy to keep it fixed in view during an exposure. Exposure times that work for typical comets risk blurring subtle details if the tracking lags for even a fraction of a second. The same factor will constrain the post-perihelion window, Once it swings past its closest point, it will recede into the outer darkness at a speed that removes it from range far sooner than most bodies on elongated loops. For scientists, the key point is that no combination of local gravitational interactions, whether with the sun, planets, or both, could impart this much hyperbolic excess speed to an object first formed here. That surplus energy is exactly what puts its inbound track above the parabolic threshold, the dividing line between bound ellipses and open-ended hyperbolas. And unlike parabolic orbits, which are just at the escape limit and no faster, this one overshoots it by a wide margin. One can calculate the parabolic escape speed for its distance when discovered, but 3I-Atlas exceeded it enough to make its extrasolar status beyond doubt. This surplus tells a larger story about its past. It points to an ejection from its home system through mechanisms capable of delivering such a boost, possibly a gravitational interaction with a giant planet or with a close stellar companion. Once freed, it would have passed through interstellar space in a path only gently altered by distant stellar encounters. For millions or even billions of years, it kept essentially that same velocity, approaching our neighborhood only because our sun happened to lie in its way. Each measurement of its position now can be run backward in time through orbital simulations, revealing probable approach vectors and setting constraints on its unknown point of origin. Because objects at this speed regime are rare to detect, each one becomes a reference point for population models of interstellar debris. Predictions suggest vast numbers of such wanderers drift unseen between the stars, most destined to pass through empty space forever. A lucky alignment lets us intercept one with our observations once in a great while. This scarcity makes every track and velocity reading valuable, not just for characterizing the object itself, but for refining how frequently planetary systems like ours eject icy bodies, and how fast those bodies escape into the galaxy. Even now, while it is still inbound, astronomers can use slight changes in its track to refine those calculations. The pattern of acceleration tells us not only about the unchanging effects of gravity, but also about any non-gravitational forces acting on it, tiny thrusts from outgassing that can subtly shift the trajectory. Monitoring this is important for confirming that its unusual speed does not hide some misinterpretation, and that every visible element of its flight fits with the interstellar scenario. In a few months, the inbound measurements will have their counterpart in outbound ones. This won't be a neatly mirrored curve, because there's no return leg. The comet will carry away almost all of its current motion, slowed only slightly as it climbs clear of the sun's gravity. Even at great distance, when its velocity stabilizes back to its interstellar baseline, it will have long since passed beyond the reach of detailed study. That makes the present interval critical. Every figure logged now becomes part of the enduring record of a high-speed traveler from another stellar nursery, captured fleetingly in transit through hours. And yet, speed is just one part of what has drawn such focused attention to 3I-Atlas. Its other defining feature began to emerge in images taken, while it was still tens of millions of miles farther out than most comets are when they wake, something that hinted at activity far earlier than expected. Signs of an active traveler. Soon after its detection, subtle but measurable changes in the appearance of 3I-Atlas began to draw attention. Within weeks, independent follow-up observations reported a marginal coma surrounding the central point of light, barely discernible, yet present across different nights and instruments, and a short tail, about 3 arcseconds in length, oriented along its trajectory. These were not processing artifacts or tracking anomalies. The effect was consistent enough to record and report. By July 21, Hubble Space Telescope imaging confirmed the picture in sharper detail, capturing a faint, teardrop-shaped dust cocoon enveloping the nucleus. Gemini and NASA's infrared telescope facility later provided supporting views, refining the profile of the coma and tail with complementary data. A coma forms when volatile ice is embedded in a comet's surface or subsurface turned directly into gas under sunlight, carrying dust into surrounding space. That cloud scatters light, giving the diffuse halo astronomers see. Radiation pressure and the solar wind then shape released material into a tail streaming away from the sun. In comets native to our solar system, such activity usually appears far closer in, often inside the orbit of Mars, once solar heating reaches levels sufficient to sublimate water ice. For ThreeIAtlas, already active at several astronomical units, the implication is different. The earliest jets may be driven not by water, but by more volatile compounds such as carbon monoxide or carbon dioxide, which require much less heat to vaporize. Detecting them remotely would suggest a volatile-rich composition and offer clues about the environment in which the comet formed. The relevance of early activity is underscored by past encounters. Oumuamua's featureless passage denied astronomers any direct sample of its interior materials. Its nature remains debated to this day. When ThreeIAtlas began to show signs of venting gas and dust before it even reached the inner solar system, it presented a rare chance to study an interstellar body in the act of losing material to space. Even a faint coma offers astronomers something tangible to analyze through spectroscopy of the gases and microscopy of the dust trapped in certain wavelengths. This shifts the target from a passive object reflecting sunlight to an active source, generating measurable emission lines that reveal molecular fingerprints. At the time of the first confirmed coma detections, the emission remained modest by usual cometary standards. The visible halo spanned only a tiny angular scale, and the tail length measured in mere arcseconds was almost at the resolution limit of ground-based telescopes. Yet persistence of shape from night to night, and its subtle growth as the comet moved inward, confirmed it was genuine. For observers, such consistency matters more than drama. It is the test that separates instrumental noise from a true physical process. Material escaping from the surface does more than produce a visible glow. Outgassing acts like a low-thrust engine, applying continuous force that can nudge a comet's path in ways gravity alone cannot explain. Astronomers monitor these so-called non-gravitational accelerations by comparing actual positions with predicted ones from orbital models. If activity emerges preferentially from one hemisphere or follows a particular cycle related to rotation, the effect can alter the spin rate or create a measurable wobble. With ThreeIAtlas, the presence of a coma makes linking trajectory changes to specific jets much more straightforward than was possible in the case of Oumuamua. Recognizing activity early changes how observing campaigns are structured. Teams can anticipate that gas and dust production will increase as the comet approaches perihelion, and plan observations accordingly. Measurements in the ultraviolet can target water vapor if and when it appears, while infrared spectroscopy can pick out emission from CO or CO2 in cooler, more distant phases. By deploying telescopes at different longitudes, astronomers can keep the object under near-continuous watch, assembling a time-stamped record of its evolving activity and relating it to distance from the Sun. The presence of a coma at such a distance also invites comparisons with the second known interstellar visitor, ThreeIAtlas. Borisov's activity was obvious and strong at distances where solar system comets typically wake, and its appearance was in many respects unremarkable, except for its trajectory. ThreeIAtlas shares that interstellar origin but began showing detectable activity even farther out. Whether that difference stems from composition, surface structure, or the way volatile layers are buried remains an open question, and one that fits directly into ongoing studies of cometary diversity beyond the solar system. From a compositional standpoint, even a small, stable coma is a breakthrough. Gas emissions carry the spectral signatures of molecules released from the interior, revealing conditions of formation and subsequent alteration. Ratios of Co to Co2, or either to water, can point toward formation zones in a protoplanetary disk, regions colder or warmer, richer or poorer in particular ices. Detecting complex organic molecules would add weight to the idea that such chemistry is widespread and transferable between planetary systems, embedded in shared galactic space. For researchers still calibrating expectations, the fact that ThreeIAtlas is active now, while inbound and visible to sensitive instruments, marks it as a cooperative subject rather than a silent flyby. Even if its activity turns out to be limited, astronomers already have more to work with than they did for Oumuamua. The dust and gas it is shedding carry with them a record of a very different stellar nursery, one we cannot visit but can study through the sample it has delivered. Every telescope trained on it is, quite literally, capturing pieces of another system. Those pieces will not be simple to interpret. The first spectra will need careful analysis to separate weak emission lines from background noise, and to account for contamination by Earth's atmosphere in ground-based work. Confirming the presence of specific volatiles will require multiple, consistent detections over time. Changes in Coma brightness or structure must be untangled from variable observing conditions. And all of this will be happening while the comet continues on a one-way path out of range. Still, this is exactly the window astronomers need to address one of the most compelling questions any interstellar object raises. With activity underway and tools in place to read its output, there is now a path to investigate not just how fast or how far ThreeIAtlas is traveling, but what it actually consists of. Facing the puzzle of composition. From the earliest confirmation that ThreeIAtlas had an active coma, attention turned to what that faint haze might tell us about the materials within. Its distance and speed hint at where it came from, but the nature of its ices and dust speaks to the environment where it formed. Composition could reveal whether this body mirrors the comets native to the solar system, or if it contains a very different mix of substances shaped in another star's planet-forming disk. Either outcome would inform how common certain building blocks are across the galaxy, and whether planetary systems tend to produce similar raw materials. The main way to probe that makeup is by studying the light from the comet. As sunlight interacts with its dust and gas, molecules in those materials absorb and sometimes re-emit light at distinct wavelengths that serve as chemical identifiers. Spectroscopy breaks this light into a spectrum, so researchers can search for patterns, bright lines or dark gaps, that match known signatures. Astronomers will be watching for water, carbon monoxide, and carbon dioxide, along with organic molecules. Each of these has its own implications. Water suggests the body formed beyond a snow line, where temperatures were low enough for ice to remain stable. Co and Co2 can drive activity at much greater distances from a star. Organics point to chemical processes that might happen widely in protoplanetary environments. In practical terms, the work involves tracking very faint targets in challenging conditions. At its current distance, the coma is still small, and the gases present may be dominated by highly volatile species like carbon monoxide. Detecting them will require large telescopes, long exposure times, and steady atmospheric conditions. Near-infrared spectrographs are key because many of the vibrational bands for these molecules lie in that range. Instruments on the ground, such as Gemini South or NASA's Infrared Telescope facility, have already reported early near-infrared hints worth further checking. Observations from space-based telescopes like the Hubble Space Telescope and the James Webb Space Telescope are scheduled as well, using their freedom from atmospheric interference to search for weak emission lines with higher sensitivity. If water vapor appears this far from the sun, it would be a notable result, pointing to a fractured or highly porous surface that lets sunlight warm buried ice quickly. More likely, water-driven activity will increase later, closer to perihelion, with the early phase powered by other volatiles. By collecting spectra repeatedly, astronomers can watch the transition, building a profile of the comet's outer layers and deeper composition. Another target will be the complex organic molecules. These carbon-based compounds are common in many solar system comets and are important in discussions about how primitive chemistry reaches young planets. Early follow-up spectroscopy aims to test for similar species in ThreeIAtlas. A positive detection would suggest that the chemical pathways leading to organics can occur under a broad range of stellar and planetary conditions, not just here. If absent, it might hint at differences in the chemistry of its home environment. Dust lifted from the surface offers a separate line of information. When sunlight bounces off these particles, it changes the light's polarization. By measuring that change, polarimetry can reveal grain sizes and surface textures. Combined with color and brightness data, these observations can narrow down whether the dust is rich in silicates, carbon, or other materials. Comparing these traits with known comets here will help determine whether ThreeIAtlas carries a familiar mix or something distinct. Extracting these signals is never straightforward. Reflected light from dust can mask emission lines from gas. Background starlight and Earth's atmospheric absorption need to be accounted for. The comet's motion adds another layer. Its velocity relative to Earth shifts the wavelengths of its features via the Doppler effect. Calibration must be precise to avoid mistaking noise for a real detection. Even so, a handful of clear identifications would be enough to reshape ideas about how much variation exists among interstellar objects. It is also possible that ThreeIAtlas could surprise us entirely. Observations of protoplanetary disks around other stars show a variety of molecules, some not familiar from our own comets. If such compounds are embedded in this nucleus, even in small amounts, they would expand the known diversity of materials forming around stars. But any such interpretation must rest on solid, repeatable evidence, which is why teams are careful not to claim results before the data are secure. The clock is part of the challenge. If early activity is driven by a thin layer of volatile ice, the coma could fade before inner layers warm enough to sustain outgassing. Missing that phase could mean losing the chance to identify certain compounds. That risk drives international coordination, with observatories planning overlapping wavelength coverage to minimize blind spots. Surface behavior brings its own variables. Gas jets can eject material unevenly, exposing fresh patches or sealing others under fallback debris. These shifts can alter the mix of gases and dust in the coma over days or weeks. Interpreting chemical changes, therefore, requires enough observations to tell apart surface geometry effects from actual compositional differences. Whatever the results, the conclusions will reach beyond this single object. If its spectrum broadly matches that of local comets, then the processes that shape icy bodies may produce similar results in many planetary systems, supporting the idea that the solar system's chemistry is not unusual. If, instead, significant differences appear, models will need to account for a wider range of possible building blocks and environmental histories. Both possibilities carry weight. Similarities would imply that water, organics, and certain minerals are widely available and potentially common in systems forming planets. Differences would underscore the diversity of chemical environments across the galaxy and raise questions about what worlds emerge from them. Even without samples brought to Earth, carefully gathered spectra can turn this fast-moving visitor into a rare probe of another star's formative processes. From here, the question is how its chemical fingerprint compares to the only two interstellar visitors studied before. Those earlier cases revealed their own surprises, one entirely without activity, the other behaving much like familiar comets. Where ThreeIAtlas falls between them remains to be seen. Comparisons to past visitors. The two previous interstellar visitors could not have been more different in behavior. Oumuamua, discovered in 2017, was small. Estimates range from just a few tens of meters to perhaps a few hundred meters long depending on the model, and entirely inert. No coma, no tail, nothing to suggest active outgassing. From the moment it was spotted until it vanished from view, it remained a point of reflected sunlight whose brightness shifted only because of its tumbling, elongated shape. With no gas or dust to analyze spectroscopically, its physical and chemical nature was left to be inferred from how it reflected light and how it moved. That absence of observable activity left the door open to many competing ideas about its makeup, from a rocky shard to an icy fragment coated in insulating material. By contrast, 2I/Borisov, which arrived in 2019, was unmistakably an active comet. It fell neatly into patterns familiar from native solar system comets: a bright, persistent coma surrounding its nucleus and a clear tail extending well away from it. Size estimates put it in the range of a few hundred meters to roughly a kilometer across. Spectroscopic studies quickly revealed water vapor, cyanide gas, and dust grains rich in carbon-based compounds. This activity and composition removed any doubt about its classification and gave astronomers the first direct sampling of interstellar cometary chemistry. With Borisov, the months-long period of visibility allowed researchers to measure how its gas production rates evolved and compare them to patterns seen in local comets. When 3I-Atlas was confirmed to be on a hyperbolic path, observers immediately framed the question in the same terms. Would it resemble the quiet, enigmatic Oumuamua or the active, comet-like Borisov? Early imaging answered that very quickly. In the weeks after detection, telescopes recorded a faint but measurable coma and a short dust tail, even while it was still far from the sun. That placed it firmly on the active side of the spectrum, more in the style of Borisov than Oumuamua, and it meant the scientific potential would be determined by how much and for how long that activity persisted. The way these three compare in size is another notable distinction. While Oumuamua's elongated body likely measured only tens to a few hundred meters in length, and Borisov's nucleus fell somewhere between a few hundred meters and about 1 kilometer, 3I-Atlas has a far wider spread in current estimates. Upper limits from Hubble imaging place its diameter no larger than about 5.6 kilometers, while lower bounds, based on brightness and assumed reflectivity, indicate it could be as small as roughly 320 meters. Even at the lower end, it ranks among the larger confirmed interstellar objects, with the potential for more exposed surface to drive sustained activity. If it is indeed toward the larger extreme, the coma could become significantly more extended and brighter than Borisov's, depending on ice composition and the distribution of active vents. Its early display of activity, while still several astronomical units out, suggests that some of its surface or near-surface ices are composed of highly volatile materials. In solar system comets, that often means carbon monoxide or carbon dioxide, which sublimate at much lower temperatures than water ice. Borisov displayed early signs of such volatile-driven activity as well, but its coma brightened in a steady, predictable way as it approached the sun. Whether 3I-Atlas will maintain that pace, surge early and then plateau, or accelerate further into perihelion is an open question, one which will frame how much data can be collected over time. Another axis of comparison is how long each object could be studied in detail prior to closest approach. Oumuamua, demure and inactive, provided no evolving features to track over time. Borisov's activity, by contrast, allowed a progressive record of gas output and dust production to be built during its inbound journey. Because 3I-Atlas was detected early and already showed signs of activity, its gas and dust production can be followed across a longer baseline than Borisov's, potentially giving the clearest picture yet of how an interstellar comet responds to increasing solar heating. The type of dust it produces may also set it apart. The short tail seen so far could indicate larger dust grains that persist near the nucleus without being quickly driven away by the solar wind, or it could reflect low ejection speeds at this distance. Borisov's dust tail was long and diffuse, pointing to a predominance of smaller particles. If 3I-Atlas is expelling larger grains, they can be distinguished by how they scatter sunlight, making it easier to separate their contribution from gas emissions in spectra. Polarimetric measurements, comparing the polarization of reflected sunlight at different angles, could reveal grain size distributions and add another dimension to interstellar comparison. Even with all these similarities to Borisov's active state, there remain aspects where 3I-Atlas is its own case. Its record-setting velocity means it will spend less time in the zone where solar energy is intense enough to produce peak outgassing. For observers, that compresses the likely window for high-activity data collection. Perihelion may bring its brightest and most dust and gas-rich phase, but that phase could narrow rapidly as it leaves the sun's vicinity. Borisov's longer period near peak brightness gave astronomers more flexibility to schedule observations. For 3I-Atlas, planning must be more immediate. The contrast to Oumuamua is still relevant in a subtler way. One of the enduring puzzles from that first visitor was its non-gravitational motion, an acceleration that could not be explained by gravity alone, perhaps caused by outgassing too faint to detect. Debate about its cause continues. With 3I-Atlas, which is visibly active, any similar small accelerations will be easier to link to definite sources like jets or asymmetric emission. That comparison may help evaluate whether Oumuamua's extra push could indeed have come from hidden volatiles, or whether a different explanation is needed. At this stage, the most straightforward classification slots 3I-Atlas in with active interstellar comets like Borisov, while noting its exceptional speed and the wide uncertainty in its size. It has already answered the simplest question posed to any such visitor. It is not another inert, featureless object. It will provide measurable activity throughout its visible paths, giving researchers direct material to analyze. As the sparse catalog of interstellar objects slowly grows, these three cases outline the range of behaviors so far observed, from inactive and enigmatic to dynamically active and chemically rich. Oumuamua marks the quiescent extreme, Borisov the familiar cometary pattern, and 3I-Atlas is emerging as the largest and most energetically active example yet. How these differences connect to their formation environments remains an open question, one that can only be approached by comparing what each carries with it as it arrives. With its origin beyond the solar system certain, the next step will be to consider not just what 3I-Atlas is and how it behaves, but the long journey that brought it here. Understanding its incoming path may offer clues about the kind of stellar neighborhood it once called home, and about how common such travelers might be in the galaxy. A path from the galactic thin disk. Understanding where 3I-Atlas came from requires turning the usual approach to tracking comets on its head. Instead of projecting its route forward in time, astronomers work backward from its current position and velocity, running orbital calculations in reverse until the path extends well beyond the solar system. This backtracking reveals the direction from which it was moving before the sun's gravity shifted its course. For 3I-Atlas, those computations point to a radiant, the apparent source point on the sky, in the direction of the constellation Sagittarius, toward the Milky Way's core. That region lies along the dense plane of the galaxy's thin disk, where stars, dust, and gas are most concentrated. The radiant offers only a broad clue. For comets bound to the sun, it doesn't hold much meaning because their orbits eventually loop back to familiar alignments. For an object on a hyperbolic trajectory, however, it reflects its incoming path through interstellar space. Even so, it's not a pinpoint. The sector near Sagittarius spans a vast range of distances and contains countless potential source systems. Any apparent straight line from the current trajectory through that region inevitably blurs over deep time, because the galaxy itself is in motion. Here is where the limitations become clear. With an inbound velocity still near 137,000 miles per hour, and an apparent hyperbolic excess speed of around 57 kilometers per second, ThreeIAtlas would cover many light years in only a few 100,000 years. Over the millions and likely billions of years since it was ejected from its home system, the Milky Way's stellar disk has undergone continual dynamical changes. Stars orbiting the galactic center at different rates, gravitational tugs from giant molecular clouds, and the subtle but cumulative influence of passing stars. These processes make reversing the path to a single parent star essentially impossible. Each distant encounter would have altered its course slightly, and over cosmic timescales, those diversions accumulate into a trajectory that no longer points with precision to a launch point. Interstellar space is therefore better thought of as dynamically crowded rather than empty. A near pass, even within a couple of light years, can bend the course of a small body without visibly disrupting anything else. Repeated small deflections act like random steps that smear out a one-straight trajectory into a probabilistic fan of possibilities. With ThreeIAtlas, we can follow a reliable track back a few million years at most before uncertainty dominates. Beyond that, the exact route becomes irretrievable. Given those constraints, astronomers focus on identifying the galactic population to which an interstellar object most likely belonged. The thin disk, about 1,000 light-years thick, contains most of the galaxy's stars younger than about 10 billion years, including our Sun. Plotting ThreeIAtlas's motion backward to just outside the solar system shows that its velocity aligns with the general flow of stars in this flattened disk. That match makes it highly probable that the object originated in a thin disk system, rather than in the thicker, older stellar populations that extend above and below it, or in the distant, sparsely populated halo. This conclusion matters for more than context. Stars in the thin disk tend to share a broadly similar chemical enrichment level, what astronomers call metallicity. That means the raw materials available in their planetary systems, from silicate minerals to volatile ices, are often comparable to what's found in our own. If analyses of ThreeIAtlas's Coma show strong similarities to solar system comets, it would be consistent with this shared environment. If instead its chemistry proves unusually different, that would stand out against expectations for thin disk material and point to local variations in how planet-forming regions operate even within the same galactic structure. The likelihood that ThreeIAtlas has been moving through the thin disk for much of its existence also constrains its age. Studies on the dynamics of such bodies suggest that gravitational interactions over billions of years slowly increase the vertical spread of their orbits, a process sometimes referred to as galactic heating. The modest inclination in ThreeIAtlas's path relative to the plane of the disk hints that it may have been part of this population for a vast span of time. While there's no precise figure, it is probably on the order of billions of years since its ejection from a home system, during which it has crossed many interstellar neighborhoods before arriving here. We cannot, and likely never will, match it to a single star in a catalog. That outcome doesn't diminish the value of reconstructing its broad origin. The region of the galaxy an object comes from thin disk, thick disk, halo, or more exotic structures, frames the likely conditions under which it formed. Thin disk comets would typically have been shaped in stable planetary systems with relatively circular stellar orbits, and could have been expelled through gravitational interactions with giant planets or close stellar encounters. In that sense, ThreeIAtlas's history could parallel what would happen if one of our distant Oumuamua cloud comets were thrown into interstellar space by Jupiter. Its path also offers an independent check on models of the Sun's own motion through the Milky Way. A hyperbolic trajectory provides a fixed reference in galactic space, allowing us to refine the vector of the solar system's travel relative to nearby stars. Comparing this with the arrival directions of previous interstellar objects can highlight whether there are preferred inflow patterns, possibly linked to how the Sun moves through denser and sparser regions of the thin disk. Another aspect of its journey worth noting is the environment it may have recently crossed. If, before we spotted it, 3I-Atlas passed through regions of denser gas or dust, it might bear surface signatures of that passage, small-scale erosion, or compositional changes that could subtly influence the makeup of its coma now. While these would be secondary effects compared to its primordial composition, they remain a potential factor in interpreting what instruments detect. In the end, the view backward is a broad map, not a precise address. The evidence points to an origin within the Milky Way's thin disk, in a system broadly similar in setting, though not in detail, to our solar system. From there, it spent a long, slow voyage weaving between other stars, never again bound to any, its surface altered only by occasional radiation and tiny impacts. The movements of the stars have erased the fine lines of its trail, leaving only the general direction and kinematic signature to connect it to its birthplace. Recognizing that origin sharpens the scientific questions we can now ask. What does a thin disk comet, shaped in a potentially familiar protoplanetary environment, tell us about the diversity or uniformity of small icy bodies across the galaxy? Will it confirm that the volatile and dust mix we see here is common, or mark this as a system with its own distinct recipe? Those answers depend entirely on the data we can collect during the short time it remains within reach. The challenge now shifts from where 3I-Atlas was born to how, and how quickly, it can be studied before it disappears from view again. Observation windows and challenges. For astronomers, certain objects impose unforgiving deadlines, and 3I-Atlas is one of them. Its hyperbolic path guarantees it will sweep through the inner solar system just once, at exceptional speed, leaving only a narrow span when it can be studied. The usable window is set not by how long it remains nearby, but by how long it stays bright enough and well-placed for telescopes to collect meaningful data. That timetable is already taking shape, and missing any portion of it means losing specific kinds of information forever. From its July 2025 discovery, the comet has been approaching from beyond Mars's orbit. In the southern hemisphere, where it was first sighted, its position against the star field will keep it within reach of major ground-based instruments for months. During this inbound leg, activity is expected to intensify as it nears the Sun, both from decreasing distance and from the increasing release of volatile gases. Brightness models suggest it could reach magnitude 15-16 in August and September, potentially within range of skilled amateur observers using moderate aperture telescopes and CCD cameras. This is always conditional. Comet brightness can defy predictions, but if these numbers hold, it offers a rare chance for non-professionals to report valuable observations alongside professional campaigns. One unusual opportunity comes before perihelion. On October 3, 2025, 3I-Atlas will pass relatively close to Mars, about 0.19 astronomical units, or 1780 million miles. While that is still far by human terms, it is a tight approach on interplanetary scales. Mars-orbiting spacecraft could, in principle, turn their instruments toward it, capturing images and spectra unobtainable from Earth's line of sight. If such observations are scheduled, they could fill in details during a period when Earth-based geometry becomes less favorable. The primary inbound phase runs until late October. During these months, high-sensitivity spectrographs will target the faint signals of ices that vaporize at low temperatures, such as carbon monoxide or carbon dioxide. Imaging will monitor the coma's size and morphology, tracking the evolution of the short tail first detected in July. These baseline measurements become essential for interpreting changes later on. The closer approach to the Sun will also refine its orbit night by night, improving precision for where it will next be visible against the stars. A sharp break arrives near the end of October. Around October 29-30, 2025, 3I-Atlas will reach perihelion, the point of maximum solar heating and velocity. Unfortunately, from Earth's vantage point, It will then appear very close to the Sun in the sky, entering solar conjunction. This glare renders direct observations unsafe or impossible for most telescopes on or near Earth, including Hubble and JWST, which must avoid pointing near the Sun for instrument safety. The result is a several-week blind spot, precisely when its activity may peak. In some cases, solar observatories like SOHO or Stereo can capture comets passing near the Sun with coronagraphs designed to block the solar disk. Whether 3I-Atlas crosses their fields of view depends on the exact geometry, and even if it does, such instruments are not optimized for the fine detail of dedicated comet missions. If coverage is obtained, it may reveal qualitative changes like increased dust production or tail length, but with lower resolution and limited spectral range. By early December 2025, the comet should reappear in a darker part of the sky as it moves away from the Sun's glare, marking the start of the outbound phase. Initial weeks after conjunction are critical. Activity can either persist, powered by slower sublimating ices, or collapse quickly as the supply of solar heat declines. Measuring the decay rate in gas and dust output offers clues to the layering and composition of the nucleus. The outbound arc will see the comet climbing away at interstellar escape speeds, making its apparent motion against the stars rapid in the first weeks. Sky separation from the Sun will improve night by night, but its distance from Earth will grow at the same time, causing its brightness to fade. Brightness predictions suggest a possible return to the 15th-16th magnitude range in November and early December, again, offering a conditional possibility for experienced amateur capture before it drops beyond their reach. Professional teams plan to use this post-perihelion period to gather the highest quality complementary spectra while the object is still active and accessible. JWST is scheduled to observe it in December, complementing inbound data it will collect in August. Space telescopes like JWST and Hubble have an advantage here. JWST's infrared spectrographs can detect molecular vibrations and heat signatures blocked by Earth's atmosphere, while Hubble's ultraviolet capability can reveal emissions from species like hydroxyl that trace water photodissociation. Combining these with ground-based optical and near-IR data deepens the compositional profile. Seasonal and lunar conditions will shape visibility for both amateurs and professionals. Dark sky periods near the new moon in August, September inbound and November, December outbound will improve the contrast needed for faint coma features. Conversely, bright moonlight could wash out detail, making careful scheduling important. Coordinated observing networks will work to balance regional weather risks and moon phase constraints, ensuring as continuous a record as possible. Tracking at this pace pushes technical capabilities. Because the comet's proper motion will exceed that of most asteroids and comets typically observed, telescope mounts must adjust rates in real time to keep the nucleus centered during exposures. Without that precision, long exposures risk smearing, especially detrimental in high-resolution spectroscopy, where weak emission lines could be lost. Not all facilities can adapt to these speeds, so the highest fidelity data will come from observatories equipped with flexible tracking software and wide enough apertures. Data coordination will aim to match inbound and outbound spectra to search for compositional shifts, measure outgassing rates, and assess whether dust properties change as surface layers are stripped away. Photometry will track subtle fluctuations in brightness that could indicate rotational changes, a known effect if jets act asymmetrically. Fine-tuning the orbital model against these non-gravitational forces can also constrain the nucleus's size, mass, and density within the limits of indirect measurement. Time is the limiting factor. By early 2026, as it passes outward past Jupiter's orbital distance, the comet's activity will almost certainly be minimal, and reflected sunlight will have faded beyond reach for even the largest telescopes on Earth. Once that threshold is crossed, no further direct measurements will be possible. It will recede into space bearing whatever information was obtained during its few months of observability, joining Oumuamua and Borisov as another dataset defined entirely by a fleeting visit. Against this narrowing schedule, each slot on a telescope, each cooperative night between observatories, and each orbital phase carries unique, non-repeatable value. The core challenge lies not in knowing what would be interesting to measure, but in capturing as much as possible before the comet escapes view for good. What remains afterward are the data points we managed to claim, a partial record of an object formed far away and long ago. Those few months of targeted work are not only about documenting a single comet's passage. They represent a rare opportunity to gather direct evidence from far beyond our own planetary system, using it to test ideas about how such bodies form and evolve. The implications of what is learned, or what is not detected, reach well past the specifics of ThreeIAtlas itself. Why we care? Until very recently, every rock, grain of dust, and shard of ice we could examine came from inside our own solar system. Even the most distant spacecraft have only sampled or imaged material bound to the sun. Our understanding of how planets form, what comets are made of, and how small bodies evolve has been built entirely on what we can measure here. That's a narrow baseline, one set of conditions from one location in a vast galaxy. An object like ThreeIAtlas changes the frame. It is not just another comet to log in a database. It is a natural sample returned from another planetary system, carrying in its dust and ices the environmental record of the place where it formed. Thinking of it this way makes its significance clear. We cannot, with any existing spacecraft, reach another star and bring back physical material within a human lifetime. But now and then, the reverse happens. Something formed far away crosses into our neighborhood. Each interstellar visitor is, quite literally, a free sample from another star system, delivered close enough for us to study with instruments on Earth and in orbit. These samples arrive without the cost and complexity of interstellar travel, and the opportunity they offer is not theoretical. The ices, minerals, and organics embedded in ThreeIAtlas are direct evidence of the chemistry and physical conditions in a distant protoplanetary disk. That alone would warrant attention, but these events are extremely rare. Since modern surveys became sensitive enough to spot faint, fast-moving objects in the outer solar system, astronomers have confirmed only 3 interstellar objects: Oumuamua in 2017, ThreeIAtlas in 2019, and now ThreeIAtlas in 2025. In that same span, we have cataloged millions of comets and asteroids native to our own system. The detection rate tells the story. Most interstellar bodies will never pass close enough or bright enough for us to see them at all. When one does, the odds of seeing an exactly similar case again soon are not high. That scarcity means each example carries disproportionate weight. Oumuamua was inert and unusually elongated, revealing nothing directly about its chemistry. Borisov looked and behaved like a typical comet from our solar system, venting water vapor and carbon-bearing gases. ThreeIAtlas has begun shedding dust and gas while still several astronomical units from the sun, hinting at a surface rich in volatile compounds. Across just 3 cases, size and behavior already vary dramatically. The lesson so far: there is no single template for an interstellar object. The practical reason for studying that diversity is that comets preserve the raw mix of their birthplaces. In our own Oumuamua cloud, many have changed little in 4.6 billion years, effectively freezing the composition of the early solar nebula in place. If ThreeIAtlas shares that kind of preservation, and its composition matches solar system comets, it would support the idea that planet-forming chemistry is broadly similar across the thin disk of the Milky Way. If instead its spectrum shows abundant compounds rare in our comets, that would point to genuine diversity in the physical and chemical conditions where planetesimals form. Either result is consequential. One points to shared building blocks, the other to wide variation in what young planetary systems produce. The implications extend further. If compositions match, it would indicate that processes like the delivery of water and organic molecules to rocky planets, believed to have played a critical role here on Earth, might be common elsewhere. That strengthens the case for life-friendly conditions arising naturally in many systems. If the mix is different, it could mean that Earth's combination of water, minerals, and organics is a local outcome, not a galactic norm. Both scenarios reshape how we think about habitability far beyond our own system. There's also a dynamic context. In our early history, giant planets scattered huge numbers of icy bodies outward. Some settled into the Oort cloud, but many were ejected entirely. If we see a similar range of material in ThreeIAtlas, it may hint that its home system had giant planets in specific orbits capable of launching it into interstellar space. The ratio of volatile ices to dust, or signs of thermal alteration before ejection, can all be indirect clues to the layout of its original planetary system. These threads of information can only be pulled while the comet is within reach of our most capable telescopes. The speed that brought it here will carry it away just as quickly, and once it fades beyond detection limits, there will be no second look. That is why teams coordinate schedules between national observatories, university facilities, amateur astronomers, and space-based platforms, making use of every possible window before it disappears. Over decades, a catalog of well-observed interstellar visitors could answer questions a single case cannot. Are volatile-rich surfaces common? Do some carry unusual organics, or lack them entirely? Is the dust fine-grained and carbon-rich like many comets here, or something else entirely? Even without physical samples, comparing independent cases builds a framework for how planets and small icy bodies form across the galaxy. Interstellar comets also underline a broader truth. Planetary systems are not isolated. Material formed around one star can be flung into the galaxy, and over millions of years, drift through the domain of another. The exchange is haphazard, but over cosmic timescales it means that solid matter circulates between systems. ThreeIAtlas is tangible proof of that exchange, a visible fragment of another system moving briefly through ours. This case is the third time we have studied such a fragment closely. Every photon it reflects or emits can be compared against the only standard we've known, our own solar system. That standard may be upheld or challenged, but either outcome advances our understanding of planet formation and the reach of life's raw materials in the galaxy. The long-term payoff is clear. What we learn from ThreeIAtlas will refine models for how often such visitors appear, what they are made of, and what their properties say about their origins. Looking ahead, the rarity of such detections may begin to change. The Vera C. Rubin Observatory, with its 10-year legacy survey of space and time, will scan the entire visible sky every few nights. Projections suggest it could find several, perhaps even dozens, of interstellar objects during its survey. That shift transforms a handful of chance encounters into the possibility of regular study, and makes ThreeIAtlas part of the early baseline for a new era of discovery. Patterns seen in future finds will be measured against what we record now. Each interstellar visitor is a free sample from another star system, but the way to turn that into knowledge is through detailed, rapid observation. Capturing spectra, imaging activity, and tracking subtle orbital changes all contribute to a clearer picture of how such bodies form and what they can bring across the gaps between stars. The more complete that picture becomes, the better we can plan for the next opportunity. And in this case, all the planning in the world could not alter the fact that we found it too late to approach it directly, a reality that frames the next challenge entirely. Preparing for the next interstellar guest. When astronomers logged the first observations of ThreeIAtlas, the calculations left no room for doubt. An intercept was not possible. By the time it was recognized as interstellar, its high inbound velocity and limited lead time ruled out any spacecraft launch. The delta V required to match its path was far beyond what could be achieved once it was already inbound. And with just a few months before perihelion, there was no realistic way to design, build, and send a probe after it. This is the same boundary faced with Oumuamua and 2I/Borisov. Each was identified too late for anything but remote observation. The capability to approach such targets exists in principle, but without very early detection, the window for any intercept closes before work can even begin. That reality is now shaping the response to whatever comes next. One concrete step is the European Space Agency's Comet interceptor mission, scheduled for launch in the coming years. Instead of targeting a known body, it will be placed at the Sun, Earth L2 point, about 1.5 million kilometers from Earth, to wait in readiness. From there, it can deploy 3 spacecraft, a main platform to serve as a communications hub and 2 smaller probes capable of closer passes toward a newly discovered target. This architecture is built precisely for the unpredictable. If an interstellar visitor is detected early enough, Comet Interceptor can start from a vantage point already outside Earth's gravity well, minimizing launch delay and fuel cost. Time, more than any other factor, governs these opportunities. Interstellar objects tend to have high hyperbolic excess velocities, V values on the order of tens of kilometers per second. They cross the detectable sky fast, and most are found only months before perihelion, when they are bright enough for current surveys to flag. In that short interval, every day lost to confirmation or planning means millions of kilometers more distance traveled and steeper demands on trajectory design. This is why a mission sitting in a ready position matters. It bypasses the bottleneck of having to escape Earth just as the target is moving fastest. For Comet Interceptor, flexibility is central. Incoming targets will vary in speed, size, and approach angle. The main spacecraft is designed to relay data and coordinate the smaller probes, which will separate an approach from different vectors to capture imaging and compositional data from multiple perspectives. They can sample dust and gas directly from a comet's coma during a high-velocity flyby, while staying close enough for high-resolution images of surface structures. It is a brief window for science, but one engineered for maximum return. The prerequisite is earlier discovery. Surveys like Pan-STARRS and ATLAS already play a role in spotting small, fast-moving objects, but their detection range means such bodies often appear in the data only a few months before they are near perihelion. A large comet entering on an interstellar path might be spotted slightly earlier, but still too late for a newly launched spacecraft to get there. Extending the detection range is the next priority. That is why the Vera C. Rubin Observatory's legacy survey of space and time is anticipated as a major shift. With an 4-meter mirror and a field of view capable of imaging the entire visible sky every few nights, Rubin will catch fainter objects farther out. Simulations suggest it could see an active interstellar comet like 3I/Atlas a year or more prior to perihelion, time enough to confirm its orbit and redirect an on-station mission like Comet Interceptor. For a fast-moving target, doubling or tripling the lead time is the difference between watching from afar and closing the distance for direct measurement. Detection is only the opening step. Once a candidate is flagged, its path must be confirmed rapidly with follow-up from multiple observatories. Those observations refine its orbit, discriminate between bound and unbound trajectories, and reduce uncertainties for any intercept planning. A delay in this stage means a spacecraft would have to carry more fuel to cover a wider range of possible rendezvous points, cutting into the margin available for science maneuvers. Successful response to an interstellar detection depends on this chain working without bottlenecks. The speed and trajectory of interstellar comets also limit mission profiles. Matching velocity for an extended rendezvous is likely impractical. Even with an early start, intercepts will be fast flybys. Instruments must be designed to cope with rapid relative motion, acquiring images and spectra in seconds or minutes. Dust collectors must be built to sample material without being destroyed by impact energies. These engineering challenges are manageable if planned in advance, but they require tailoring to mission timelines counted in months rather than years. Even if a probe is not dispatched, early discovery has huge benefits for Earth and space-based observation. It allows telescope time to be reserved across different wavelength bands, from radio to ultraviolet, following the object through its entire approach. Observatories like Hubble and JWST can be queued for target of opportunity campaigns, something difficult to arrange without months of warning. A coordinated, multi-wavelength approach extends the science return far beyond what isolated observations can achieve. ThreeIAtlas illustrates both progress and present limits. It was found early enough for months of remote study, a marked improvement over Oumuamua's post-perihelion discovery, but still far too late for any physical intercept. With facilities like Rubin coming online, the number of cases detected in time for a spacecraft rendezvous should rise. Each additional year of lead time expands the envelope of what can be attempted, from better targeted flybys to comprehensive mapping of an interstellar comet's physical environment. The payoff, if all pieces align, is direct data from a body formed around another star, images of its nucleus with meter-scale resolution, mass spectrometry of fresh volatiles, particle analysis of its dust. This information would bridge the gap between our indirect measurements and the kind of close-range science now familiar from missions to solar system comets. By linking those samples to their orbital history, scientists could infer the properties of the planetary system that produced them. The infrastructure built for such missions can serve double duty. A spacecraft on standby for an interstellar comet could just as well be sent to a rare Oumuamua cloud comet entering the inner solar system for the first time, or to an asteroid flagged as a possible threat under planetary defense protocols. In each scenario, the core requirements, early detection, precise orbit determination, rapid launch readiness, and robust flyby instrumentation, are the same. Investments in readiness, therefore, spread across several high-value targets. Developing this capability is not just about the occasional high-profile discovery. It is about ensuring that when the data gap between see it and study it up close narrows, we have the means to cross it. The decision to position Comet Interceptor at L2 reflects that shift in strategy. Prepare in advance, wait, and move without delay when the opportunity presents itself. The more often we can do that, the less often we will watch unique objects slip away with their secrets intact. We cannot close the distance to ThreeIAtlas now, but every lesson from its discovery, tracking, and missed intercept feeds directly into the next attempt. The ability to act during the short window after discovery will depend on how well detection networks, follow-up observations, and mission assets are integrated. That readiness will determine whether the fourth interstellar visitor is just another point of light or a source of in situ data we can actually hold. We can't chase this one, but we're learning fast, so the next time one comes, we may be ready. And that readiness changes how we see these visitors, setting the stage for what they reveal about a galaxy where such exchanges are always taking place. ThreeIAtlas is the third confirmed interstellar object, arriving with early cometary activity, an inbound speed near 137,000 miles per hour, and a one-time passage that will take it permanently out of reach after this orbit. It is direct, physical evidence that material from another star system can survive the journey intact to our own, carrying clues to conditions far beyond the Sun's domain. Its brief visit offers a scientific payoff that will not come again for this object. If you want updates as observations come in, like and subscribe, and in the comments, tell us, what would you most want from an interstellar comet discovery? New molecules, a nucleus image, or something else?